Okay, this video segment deals with the contents of chapter 15 of the textbook Finite Element Essentials in 3D Experience. Uh, it is dealing with the harmonic response of a simply supported beam. So let me explain to you what I have in mind. So suppose you have a bar as shown below, or a beam as shown below, with a given cross section, and it's simply supported, as you can see. And right at the middle of this, or somewhere else, it doesn't have to be the middle, there is a sinusoidal load that is acting. If you think, how could this be true? Well, imagine that there's a motor turning at a given speed, and there's an unbalance associated with the motor, which is always the case, and therefore there's a sinusoidal load that is applied, harmonic load that is applied at the middle point. I'm going to be assuming that this is a linear elastic material, so we're dealing with Young's modulus, Poisson ratio, and we need the density too, because this is a dynamic problem. You need natural frequencies, and we're going to be needing the density. The length of the beam is 1,000 millimeter, a meter, think about it like that, and it's divided into 20 elements, and the cross section is circular. Now, it is possible to do the problem where you have a full length of the beam modeled as a line and divided in 20 pieces. Uh, but in order to do that, you need a feature created right at the center of the beam. So it's easier if I did it as two lines. The first 500 millimeter is one line. The next 500 millimeter is two lines, line two, and then you divide that. Okay, because then there's a guarantee there is a point in the middle that you can apply force. So in order to ensure that it's simply supported, we need special kind of conditions at the end. And to ensure that this is a two-dimensional problem with vibration in the YZ plane, I'm going to assume that this entire bar is prevented from moving in the X direction. Okay, so we get to this thing later on. We have to ask for some additional information because we want to plot the displacement of the center point as a function of frequency. Okay, so we'll see. Okay, so let's go ahead and create a model. We're going to create 3 points to begin with. We're in part design, so essentials, 3 points. Point number 1, coordinate is 0, 0, 0. Point number 2 with a y of 500. And number 3 with a y of 1,000 mil. Oh, these are millimeters. Millimeter. Okay, so let's go to point number 2. Accidentally, I put down 500 meters. So, oh no, that's good. 500 millimeter, very good. So where are these 3 points? There should be 3 points here. Yeah, 1, point 1, point 2, and point 3. Now we're going to need lines. Line 1 going from point 1 to point 2, and line 2 going from point 2 to point 3. Okay, let's apply material properties to this part. So under tools, material property, create, say harmonic response, harmonic response. Okay, it's going to create a shell for us called harmonic response. Okay, it is right here, so I can input my numbers right here. Right click, simulation, structural, abacus multiphysics, density 7800. I think that's what it was. This is for steel. And then mechanical, elasticity, elastic, 200 gigapascal, GPa, and Poisson ratio 0.3. 0.3. That's pretty much it. And then right click, apply. We don't need this window anymore. We apply it to the part. and a check mark, and we are ready to go. So let's save everything. Now, because the cross section of this beam is going to be circular, I don't need an orientation point. I don't need an extra point. So keep that in mind. Okay, so that's pretty much it. So let's go ahead to structural model, structural model creation, structural model creation. Nothing fancy is going to happen because first of all, let's check this back to main body. Okay, main body. Okay, say okay. Nothing fancy is going to be here because this is no solid model that is going to mesh it automatically. Okay, so I have to do all the meshing myself. So the first thing that we're going to do, we're going to go to a mesh, and we're going to need a beam mesh right there, beam mesh, and we select this line, and we put let's see, I need 10 along that. So see now, this was 500 millimeter. I need 10 elements, so 50 millimeters mesh. There is a 10 elements, and then repeat it for the other one. Something I wanted to remind you about, make sure that this capture node is on, because what it says is that any two nodes which are within 0.1 millimeters of each other are going to get merged. If I'm not careful here, there will be multiple two nodes at this interface, but that's going to cause a problem. Okay, mesh? All right, good. So that's this. And then we're going to create a cross section of this beam. Okay, so let's see now. We go to model. You have to go to model. Under properties, we have to create a profile for that beam. So it's going to be circular beam profile, circular, and of course the radius. I think I said 10 millimeters, right? Radius of 10 millimeters. And this is going to be used for both these pieces. So then we're going to go to do beam section. Let's take this one, and the profile is going to be profile 1, which was a circle, and there it is. Okay, notice that I don't need the orientation geometry because this is just a circle. We say fine, and then repeat it for the other one. And profile, beam profile is a circle. Okay, that takes care of what we need here. I don't think we need anything else. So now we're going to go to create scenario, structural scenario creation. It's a structural problem. All right. Now these are both red. So the first thing I'm going to do, I'm going to select my finite element model. This is the stuff that I created. These are the elements that I created. Take fine. This thing turned green. We're going to create the procedure. Now the first step, let me extract the first two natural frequencies. Okay, the first step is going to be, what is that? Is it this one? Frequency step. Okay, frequency step. So we're going to extract, I think in the book I did two modes, but that's fine. I'm going to do 10 modes here. It really doesn't matter. And this is fine. Notice that this turned green now. And now we're going to do the restraints. But first of all, if these things are bothering me in order to pick the the lines and things like that, so let me do the following. I'm going to hide the sections properties. I'm going to hide it. Right click hide, and I'm going to hide the elements, by the way. So hide the elements. The elements hidden. Okay, and there are 3 points that are created. Some software, if you put a load on this point as opposed to the vertex of the line, it will not take it. So let me hide these to avoid making any potential mistakes, because I don't think, well, I'm not 100% sure whether uh, here we have to hide it or not, but I'm going to hide it just to be on the safe side. Okay, so now we're going to go do the strengths. This endpoint, this is a pin. Okay, so cannot move in the direction X, Y, Z. Okay, and it cannot rotate about X. It can. It's a simple support. It can rotate about X, but not Y and Z. That's what a simple support is. And the other one on the other side, on this side, this was on a roller, so it can move in the direction, let's see now, direction Y. It can move in the direction Y. Yeah, it can move in the direction Y, so X and Z are fixed, uh, but it cannot rotate. Again, it can rotate about the X-axis, but not about Y and Z. So that's what a simple support is. Now, to make sure that this does not come out of plane, so let me uh, insist that this line and that line, they do not move in the direction X, so that it remains in the YZ plane. Okay, so save everything. We are ready to simulate. He asked for 10 frequencies, so simulate. Let's do a scenario check. Okay. Let's do a simulation check. Any error messages or warnings that may potentially be associated with this particular model are going to pop up here, if there are any. It's a very simple problem. I doubt it that we have any issues. Because of the restrictions that we put in the out of plane motion, and some of the endpoints is that we're not going to have any torsional modes or out of plane modes, so that's fine. And finally, we're going to run it. I'm going to get the 10 first frequencies, so the first 10 frequencies and the associated modes. Okay, so let me close this. So these are the different modes. Let me put this thing in the different view, in the XY view, because that's all we're extracting anyway. Okay, so XY view. So this is the first mode, second mode, third mode, fourth mode, etc. Okay, so let's now go ahead and create another. We're done here, so let's go back to scenario. Either I can click on the tree, branch of the tree, or go from here. Right there, go back to that interface right there. Okay, so we want to do another one now, another procedure based on harmonic response right there. Harmonic response, see that? Harmonic response. Okay, so here we're going to say, we're going to fill it in according to this table that I have here. So sweep basically between 0 hertz and 200 hertz at increments of 1 hertz. So that's what the way harmonic response works. You give it a range and how closely you want these things to be. 0, 200, and 1. So that's going to be 0. Lower limit is 0. This is 200 hertz, and this is 1 hertz. And use all the modes, okay, all the 10 modes, that I extracted. Say okay, and Oh, we apply the load. Where is the force here? Load, okay, a force on this middle point in the direction Z. It doesn't matter whether you say up or down. So I put down, I think it was 4,000. Let me see for a second. It was 4,000, yeah, 4,000 Newton. Okay, 4,000. And that's it. Okay, so we on the simulate, we ask for some extra data. The extra data being actually the displacement at this point, because we're going to have a plot of displacement of that point as a function of frequency. See that? If you go here, we want to take that vertex and extract displacement. That's all we want right now. So let's go here. Click on this. So we want displacement at this location, just the displacement. And this is not, yeah, that's a field, it's not history. Okay, history means as a function of time, right? Oh, as a function of time or frequency. I'm sorry, you need history. Okay, time or frequency is referred to history. Okay, and we say okay, and now we're gonna run it. So there's no need to do these things, but let's go ahead and do that first. First the model, then the scenario check. It's always a good idea to do these in case there's any potential warnings or error messages. There was a warning here. Let me see what this thing says, by the way. Yeah, that's okay. It slightly changed the frequency from 0 to a tiny number, so that's fine. Looks like it doesn't have 0. It doesn't like 0. Okay, that's done. And then we're gonna go and simulate it. Okay. Now this could have been done with a solid model, solid elements, etc. The only thing is that you don't have the cross-sectional properties that you have to specify. You let the software do all 3D calculations for you. While this is running, I say yes. I think I said yes. Yeah. This is fine. Okay, while this is running, let's see how we plot this thing. I think the plotting step is, well, we'll find out. Yeah. Okay, once again, the steps are all outlined in the book. So we have here, so we close this. Okay, so in order to get the plot of displacement of that function as a function of frequency, we need to go to plots. We need to go to the XY plot from history. And let's see now. What do we want? We want displacement translation, either the magnitude or displacement in the direction Z, which is, you know, this doesn't have any out of plane displacement, so it doesn't matter. Magnitude is fine, and then we're going to say apply, and there we are. Okay, notice that we had some frequencies, and this means that around those frequencies there is resonance here. So in that range that I did the calculation sweeping 0 to 200, this is the only frequency that was present. Now I didn't bother checking where the other frequency. Oh, yeah. So my guess is that let me see for a second. You can actually move the bar here to find out what that frequency is. It's right there. See that? So that. Uh, How do you move this? Sorry, just click on it. Yeah. So this is around, it looks like, I'm having a hard time reading it, but it looks like it's 39, yeah, 39 hertz. So I must have had a frequency around, let me see now, around 40 hertz. Okay, so that takes care of it. Good luck, folks.